Hey guys, welcome to this short video on mathematical notation, and in particular we'll be looking at the Sigma-Summation notation, which is used for very long sums, the pi multiplication notation, which is equivalent but for multiplications, and the lesser known Einstein-Summation notation, which is oftentimes used in vector calculus and of course general relativity. For each of these symbols I will explain what they represent, and then we'll look at some exercises to get a better understanding. And for each case you can find the timestamp in the comment section below. If you learn something from these types of videos, consider giving them a thumbs up, which helps out tremendously. Let's now go to the first case where we look at Sigma-Summation. And sigma, by the way, represents the capital Greek letter with our equivalent of S. Let's first look at an example to see what it exactly represents. Let's say that we want to add all of the odd numbers from 1 to 99. So we have 1 plus 3 plus 5 plus 7 plus and so on, all the way up to 99. And these are, by the way, 49 numbers that we want to add up. And this results in a very long summation, which I avoided writing out entirely with these 3 dots right here. And now we ask ourselves, how can we write this in an even shorter notation? Well, this is exactly where the sigma notation comes in. What we will first do is to give each position in this long series a general representation. For the first number, we denote it as A1. For the second number in the sum, we denote it as A2. For the third number in the sum, we have A3, and by now you get the picture. So we can denote every term in this long summation with a general notation, A with a subscript, the position in this series. And it's very important that you do not confuse the actual value of the number in a certain position and the number of that position. I mean with this, for example, here we have on position 2 the value A2, and the value A2 in this case is 3. Likewise, for example, here on position 4, so we have 1, 2, 3, the fourth position, we have the value 7, and so on and so on. So now that we've written all of these numbers in our series as a more general form, we can rewrite it using the sigma summation. And this looks as follows. So we have the sigma summation, which takes some practice to draw correctly. And then after the summation, we write this general term in our series, AI. And then this I is simply a placeholder. It should be 1, 2, 3, 4, and so on. And to denote this, that this I should be any index from our first index to the last index, we write beneath the summation symbol the index. So I starts at 1, because our first index is simply 1. And then above the symbol, we write 49, because the last index in our series is 49. Now again, do not confuse this 49 with the actual value at this place in our series. And there we have it already. This is a very compact and general way to write this series of 49 terms in a very simple compact notation. However, at this point, this AI, so the ith term in our series, is still not clear. With which I mean that from this notation that we have, we can still not get back to this original sum. Therefore, to do this, we still have to write this AI as a function of the ith position. And for adding all of the odd numbers, we know that for the ith position, we have to multiply this positional index by 2 and subtract 1. We see here, for example, for the first index, A1, we multiply 1 with 2 and subtract 1. This gives us 1. For this second position, we have 2 multiplied by 2 is 4, minus 1 indeed gives us 3. For the third position, we have 3 multiplied with 2 gives us 6, minus 1 gives us 5. For the fourth position, we have 4 multiplied by 2 gives us 8, minus 1 gives us indeed 7. And therefore, we can represent each term in this long series by multiplying the positional index by 2 and subtracting by 1, and then adding all of these together. So we can rewrite this summation as the index starting again from 1 and ending at 49. And now this general AI term can simply be replaced by the following. So we had to multiply our index number by 2 and then subtract 1. And this is exactly what this sum represents in a very compact notation. We start from I is equal to 1. So we fill this in. We have 2 times 1 is 2 minus 1 is simply 1 again. And we indeed get our first term in the series. And this can be done for each I going from 1 to 2 to 3 to 4 all the way up to 49. And this is exactly how this sigma summation works. So let's now look at some other examples to drive this home. Let's say that we have the sum 1 plus 4 plus 9 plus 16 plus 25 and so on. And so the first thing that we need to do is to find a pattern in this series. We have 1, 4, 9, 16, 25, and we want to find a pattern that links the index of each term. So this is index 1, this is index 2, this is on the 3rd position, on the 4th position. So we want to link this positional index with the actual value that there is. So we have here our first index, second index, index number 3, 4, 5, and so on. And then we add all of these together. However, we're not done yet because this is clearly not the same series. However, if we square each index number, we see that we indeed get our values again. 1 squared gives 1, 2 squared gives 4, 3 squared gives 9, and so on. Having found this pattern, we see that we can write it now with the sigma summation with I starting at 1, because we are starting at the first index, the first place in our series, and we end at, well, infinity, because there's no end in our original series, therefore there is no ending index in our series. So we just keep on adding forever. And so what do we write inside of the summation? Well, simply our prescription, that we have to take our index number and we have to square this to get the actual value. And this is now, again, how we write our infinite sum of squares of natural numbers in a more compact way. Let's now look at one more example where we go the other way around. So we are given a sigma summation prescription. So n in this case goes from 0 to infinity, just to show that this I is just a placeholder. I've written here I going from 1 to 49 and here I going from 1 to infinity, but this I simply is a number which represents the place of the number in the series. So it's just a summation index and you can call it any way you want. And in this case, the prescription is x to the power of n divided by n factorial. How does this series actually look like if we want to expand this sigma summation notation? Well, we simply go from n is equal to 0 all the way up to infinity, but we will truncate this sum at some point. So n is equal to 0. Let's just fill this in. So we have x to the power of 0 divided by 0 factorial. And by the way, 0 factorial is of course 1. Then the second term in the summation, we go to n is equal to 1. So we have x to the power of 1 divided by 1 factorial. Then the next term, we go to n is equal to 2. So we have x to the power of 2 divided by 2 factorial. Of course, the next term will be x to the power of 3 divided by 3 factorial. And we continue adding terms like this endlessly. And it turns out, which I will leave for another video, that this infinite summation is actually simply e to the power of x. And at this point, I hope that you're now a bit more familiar with how to interpret this sigma summation. So now that you have a better understanding of sigma notation, we can go to the next symbol, which is the pi multiplication. And with the knowledge of the sigma summation, pi multiplication will be much more straightforward and easy to understand. The first thing, again, is to go to an example. Let's say now that instead of adding the first 10 numbers together, we want to multiply the numbers from 1 to 10. So we have 1 multiplied by 2, multiplied by 3, times 4, times and so on, and eventually times 10. And again, we want to find a more compact way to write this long multiplication. The first step, of course, is to again denote each term in our multiplication with a general placeholder that has as a subscript the index of the place in the multiplication. So for the first place we have A1 multiplied with the second place A2, multiplied with A3, multiplied with A4, all the way up to the 10th place, A10. And at this point it might be a bit confusing that these indices always correspond with the actual values of these numbers in this multiplication. However, this is of course not always the case. These subscripts here simply denote the place of the number in the multiplication. This is the first place, this is the second place, this is the third place. However, the values on these places can of course be any numbers you like. However, in this specific example, they also correspond to their positional index. Now we can write this multiplication of 10 numbers simply as writing a capital Pi, which is the capital letter P in the Greek alphabet, and again the general placeholder AI for the number on position I in our multiplication. In this case, I goes from 1 to 10, and we know in this specific case that AI, the value of the number on the ith place in our multiplication, is simply the index itself. On the place with index 1 we have 1, on the place with index 2 we have 2, and so on. So this will simply be capital Pi. We start at 1 and we end at 2, and we simply have I, the index of the number at position I. And in this sense, this pi multiplication is completely analogous to the sigma summation. Let's look at an example. We want to multiply 1 with 1 over 2, multiplied with 1 over 3, multiplied with 1 over 4, multiplied with 1 over 5, and so on without any end. Therefore, we can write this as the pi multiplication, where we start at I is equal to 1. We do not have an ending index because we simply multiply terms all the way up to infinity. And now we want a prescription of how to find the value on the ith place. We see that on the first place in our multiplication with index 1, we simply have the value 1. On the second place in our multiplication, so with index 2, we have the value 1 over 2. On the third place in our multiplication, so with index 3, we have 1 over 3. On the fourth place, we have 1 over 4, and so on and so on. And you probably get the picture that the value for each number in our multiplication is simply 1 divided by the index that this number takes in our multiplication. And we see here that if we indeed fill in I going from 1 all the way to infinity, that we indeed get this series again. In the second example, we go the other way around. We start with the pi multiplication notation, with I starting from 0 to n minus 1, and the prescription is n minus I. So how do we now expand this compact notation? Well, we simply start with the first term, which is where I is equal to 0. So we have n minus 0, which already gives us the first term in our long multiplication. Then we multiply this with the second term in our multiplication, which is with I is equal to 1. All right, so we write n minus 1. Then we multiply, of course, with n minus 2, because for this term I is equal to 2. We multiply with n minus 3, all the way down to the very last term, where this index I is equal to n minus 1. So we have n minus I, but I is simply n minus 1, so this becomes minus n plus 1. Rewriting this even further, we have n minus 0 is simply n, multiplied with n minus 1, multiplied with n minus 2, all the way up to n minus n is 0 plus 1, so all the way up to 1. And we see that this multiplication can be even written in a more compact way than this pi multiplication, because we recognize this multiplication simply as n factorial. Let's now go to the third and final notation, which is much less known but nevertheless quite handy. It is the Einstein-Summation notation, and as the name already indicates, it's invented by Einstein during the time where he was working on his theory of general relativity. And this is also one of the main topics in physics where this notation is actually used. And again, we start off with an example. Let's say that we have a vector W, which is a one-row vector with components 3, 2, 1. And we have another vector, vector V, which is a one-column vector with components 1, 2, and 3. What we want to know now, or get a very efficient notation for, is the following dot product between vector W and vector V. Let's look at how this multiplication works. We have the vector W, so 3, 2, 1, and we multiply this with the vector V, which has components 1, 2, 3. This, of course, as we all know, becomes the following summation. We have 3 multiplied with 1, which are basically multiplying these two terms together. We add to this 2 multiplied with 2, which is the multiplication of these two terms. And we add to this 1 multiplied with 3, which is of course the multiplication of these last two numbers. Now, is there a way to write this in a more compact form? What did we actually do? Well, we first multiplied the first two components of both vectors together. We added to this the multiplication of the second components of these two vectors together, and then we added to this at last the third components of both vectors together. So how can we write this in a more compact way? Well, Einstein decided to write it in the following way. We have Wi, Vi, where for the first vector we have I as a subscript, and for the second vector we have I as a superscript. And the rule is that if we have an expression where we have repeating indices at a different level, so one is a subscript and one is a superscript, then we sum over the components of these two vectors. And now what this basically is an even more compact way of writing the summation. We have I is equal to 1 all the way up to 3 of Wi, Vi. We could have written it like this, because this is exactly what is written here. We multiply the first two components with I is equal 1, then we add to this the multiplication of the second components when I is equal to 2, and the same for 3. However, Einstein decided that always writing this summation is a bit tedious. Therefore, what he did was lift this index above, and there we have it, we have the Einstein-Summation notation. Now you might object that this only makes the thing more confusing. Why would you drop the symbol sigma? Well, it's that in some calculations, and more notably the calculations that Einstein was doing in the time where he was developing general relativity, is that in these calculations you would otherwise have to write a lot of sigma symbols, and this would just be too cumbersome. One example of this is the following. And you're not supposed to really understand what it means that I will be writing, but it just shows you that sometimes you need a lot of sigma symbols, which then it makes more sense to just drop them. So we have g of ij, g of kl, multiplied with ej, el. And this is a more compact way than having to write two summation symbols in front of it to sum over j and l. And therefore, we simply drop these symbols and we simply note that we, in this case, have to sum over j, because there's one j up and one j down, and we have to sum over l, because there's one l up and one l down. Another example is to calculate the infinitesimal distance in four-dimensional spacetime. This infinitesimal distance, which we denote as ds squared, is simply equal to dxi multiplied by dxi. And in this case, we have to sum over the i's, because we have one I down and one I up. And this, in a nutshell, is Einstein's summation notation. And I can fully understand that you won't be using this for quite some time, because for physics students, it's only introduced when they start with general relativity, which a large part of physics students actually never take. However, here we will eventually get to general relativity, but that's for another video quite some distance in the future. And this brings us to the end of this short video, and I hope that you're now more familiar with what these symbols actually mean. If you enjoyed this video, give it a thumbs up. If you have any questions, leave a comment in the comment section down below. If you want to get notified by future releases, consider subscribing. And with that, I thank you for watching, and I will see you in the next one. Bye.